This video covers section 2.1 functions. For those of you that took college algebra last year, this entire section should be review. However, one objective in particular we want to pay close attention to, which is finding the difference quotient. We did all of these things last year, but there are some examples, I think, in this section that are a little bit trickier than what we did last year. So if you're going to skip forward to anything, this is the thing you want to make sure you pay close attention to. So let's start with the first objective though, just determining whether a relation represents a function. So in order to do that, we need to know what is a relation. Well, I'm not going to read you all this text. Basically, a relation is just a mapping between two sets. You have any two sets and you have some kind of mapping between them that constitutes a relation. One way to think of a relation is as a set of ordered pairs. So any of these mappings could be written down as a set of ordered pairs. So as an example, this first one here, the first ordered pair would be Alaska, would be the input, and then the output is 1. And then you could just go through and do the same thing for all the other mappings. So Arizona, 9 would be your second ordered pair. So any mapping between two sets or any set of ordered pairs automatically is a relation. The set of all inputs, or for us, the set of all x values, are the domain, and then the set of all y values is the range. So for each of these relations that you see down below, it says identify the domain and the range. Well, this is your domain, and this is your range. Now you're probably going to write these as sets using the braces, but let's not go through that for each one. So for the second mapping, there's your domain, there's your range. Here's your domain, here's your range. So it's just input is domain, and then the output value, what it's getting mapped to, is the range. Okay, so a function is just a special type of relation. So a function is still a mapping, but it is a mapping so that if you take any single domain element, it gets mapped to only one range element. In other words, any input value, there should only be one arrow leaving that input value. And that is true for this mapping here. We've got 3 different input values, and they all go to one output value. It's okay if 2 different inputs go to the same output. That's okay. What we can't have is something like this, where a single input has 2 separate output values. That would not be a function anymore. Still be a relation, but wouldn't be a function anymore. Okay, so for this example, they again, we're supposed to state the domain and range. We're not going to do that again. Domain is just the x's, or the inputs. The range is the outputs. But then it does say determine whether each one is a function. So basically what we're looking for is as long as there's not 2 arrows leaving an input, meaning if an input gets mapped to 2 different places, then it's not a function. For this one, we can see 1 arrow leaving each input. So this one is a function. If we look at the next one, again, each of these gas stations has only 1 arrow leaving it. The fact that Shell and Citgo both go to 329 doesn't matter. You can have multiple inputs go to the same output. We could have every one of the inputs go to the same output, but you can't have 2 gas stations giving you 2 different prices in this case. So this one is still a function. Okay, then if we look at the last one here, this one is not a function, and it's because of 0.71 carats. It's getting mapped to 2 separate prices. We have a single input that is mapped to 2 different range elements. So this one is not a function. Okay. All right, so we said that relations can be represented as sets of ordered pairs, and so can functions. So one way to think of this set of ordered pairs is it's a mapping between 2 sets. The inputs are all the first coordinates, so the inputs are 1, 2, 3, 4, and then the output values are, we'll just put them in the same order, 4, 5, 6, 7, and then the mapping is just doing this. All right, so this set of ordered pairs is the same as this mapping that you see here. And again, we're supposed to state whether it's a function or not. And in this case, you can see that it is. For every input, it gets mapped to one and only one output. So it is a function. Now, it does also say state the domain and range. We'll do it for this first one, but I'm not going to keep doing it for each one. So the domain is the set of all x's. It's just this exact set here. So 1, 2, 3, 4. And then the range is the set of all output values. So 4, 5, 6, 7. Remember that sets, domain and range are sets, and sets need to be written with these curly braces here. Okay, next one. So let's do this one without doing the mapping here. So basically the idea is this: no input value can be used more than once. In other words, none of the x coordinates can show up twice. So that's really all we have to look at. We don't need to look at the y's at all. Just look at the x's. Each x is unique. 1, 2, 3, 6. No x is repeated, so therefore it is a function. And again, your domain would be the set 1, 2, 3, 6. The range, now let's actually write down the range for this, because with sets, there are no repeated values. So we don't write 4 twice. It would just be 4, 5, 10. That would be the entire range. We don't duplicate things when we're dealing with sets. Okay, last one. We want to know, is this a function? So we look at each of the input values, and we notice -3 is used twice. In other words, -3 gets mapped to 2 different numbers. It gets mapped to 9 here, but it gets mapped to 8 here. We have an input that gets mapped to 2 separate outputs. So this is not a function. Right, 2 different, or the same input gets mapped to 2 outputs. Now it still has a domain and range, and that still works the same way. Its domain is -3, -2, 0. You don't repeat the -3 again. And the range is still 9, 4, 0, 8. So this is what we call a discrete function, because its domain and range are finite sets here. And so one way to tell that it's can't be a function is its domain is smaller than its range. You've got more things. One of these is going to have to go to 2 separate elements, so not going to be a function. Okay, next example says determine whether this equation defines y as a function of x. So when we say y as a function of x, we are saying this is the input, and this has to be the output. Now, if you go to the textbook and look this example up, they give a written explanation as to why this does indeed define a function. I don't love their description, but I would say my argument's more rigorous, but you may not really like my argument either. So one way to think about a function is that it's saying that any time that you have 2 different outputs, so I'm going to write it this way: f of a is different from f of b. Okay, so I'm using function notation here. If you haven't seen this before, I do believe we review this a little bit later. So we're just saying, suppose you have a function y equals f of x. So we're saying if you plug in a, this is the output value. If you plug in b, this is the output value. So one way to define a function is to say if f of a is different from f of b, if you have 2 different output values, the only way that can happen is if you have 2 different input values, meaning a and b would have to be different values. Because otherwise, if a and b were the same, and this would say they get mapped to 2 different outputs, and that can't happen when it's a function. You could use this to prove this equation is a function, but it's going to be easier to use an equivalent statement to this. This is a conditional statement. This is an if-then statement, and if you remember, the contrapositive is equivalent to a conditional statement. We get a contrapositive by reversing these 2 things and negating them. We flip it and we negate it. So what's logically equivalent to this would be to say, suppose if a is equal to b, then we would need that f of a is equal to f of b. If you can establish this, this also proves that this equation would generate a function. So let's start with the hypothesis. So we're going to say let a equal b. So it's a weird thing to say. We have two numbers. We're really starting with the same number, a and b. Okay, now we can use properties of algebra. So if I have an equation, I know that I can multiply both sides by 2. Right? That's the multiplication property. So this would be true. And then I can also subtract 5 on both sides. 2a minus 5 would have to equal 2b minus 5. Right, just that's the subtraction property. This is precisely the definition of f of a. Right? I should have probably at the beginning, I should have said let f of x equal 2x minus 5 just to establish that. So by definition, this would be f of a, and this would be f of b. So we started with the hypothesis, we assumed this, and we proved that indeed f of a has to equal f of b. So therefore, y equals 2x minus 5 defines y as a function of x. Okay, it's kind of not a very satisfying answer. We're going to have a different way of looking at whether this defines a function, but this would be the strict way using just the definition. Okay, let's look at a different one. So again, another equation. It says determine whether this equation defines y as a function of x. Now, hopefully you're already saying, no, that can't be a function, because I remember this is the equation of a circle centered at the origin of radius 1. And as we'll see later, a circle cannot define a function, because if you picked that to be the input value, it gets mapped to two separate output values. This input has two separate outputs, so it's definitely not a function. But we should still be able to answer this question even if you didn't know what the graph looked like. So to do that, we can prove does not define y as a function of x just by inspection. So notice the point 0, 1. 0, 1 satisfies this equation. I know that because I can just plug it in. 0 squared plus 1 squared, that's definitely equal to 1. So that means that point is on this curve. It's on here somewhere. But I know that 0, negative 1 also satisfies. Right, and we can check it by inspection. 0 squared plus negative 1 squared. Make sure you have the parentheses on that. That is also equal to 1. 0 squared, that's going to be a positive 1, so that also works. This is a problem. We can't have this. Right? We have an input, 0, that gets mapped to two separate outputs. An x value that has two different possible y values. So therefore, x squared plus y squared equals 1 does not define y as a function of x. Okay. So, function notation. So something I've been using, I've been cheating already, but if you haven't seen this before, when we use f of x, this is not saying multiplication. It does not say f times x. F is simply the name of the function, and then this is the input, or you could call it the argument of the function. So what's being plugged in, what's being evaluated, and then this is just the name of the function. A lot of times people think of functions like a machine. You put an input into the machine, this machine's name is f, and it spits out an output. The output is a y value, but you can also denote it using f of x. The benefit of this notation is it allows you to name multiple functions, different functions with different names, and it tells you what you're actually plugging into it. So as a more concrete mathematical example, here they're looking at the mapping of f of x equals x squared. So for example, if I wanted to do f of 3 in this particular example, well, that's 3 squared, which is 9. Plug 3 into that function, you get 9 out. Common letters used for the names of functions, FGH or capital F, capital G, capital H. And capitalization matters. They are different. Capital F and lowercase f would be different functions. So we don't want to interchange them. they would just recognize that they do represent different functions. Okay, so let's try a few examples of this. So we're using this definition of a function, f of x equals 2x squared minus 3x. First one, we're supposed to do f of 3, so we are literally just plugging 3 into that function. So when I see this function, the way I think of it is I think of the x's as being input boxes, just like the input boxes that you have on Math Excel where you have to type in your answers. So this is how I see the function. And in this case, if we're doing f of 3, 3 goes in each of those boxes. So it would look like 2 times 3 squared minus 3 times 3. And then we evaluate. Make sure we're using order of operations, so we need to square first. So we have 2 times 9 minus 9. That's 18 minus 9, which comes out to 9. So f of 3 is 9. Okay, the next one's a little more complicated. It says take the function f of x and add f of 3. Well, f of x is simply just this. So we write the function back down, 2x squared minus 3x. It's saying just put x into it, okay? Well, we did that. And then we add f of 3. Well, we just found f of 3. f of 3 is 9. And that's it. You can't do anything else with this. This is fully simplified. These are not like terms, so that's it. That is the answer for that one. Okay, so then the last one, just move it over a little bit, is 3 times f of x. So, okay, so this one, you have 3 times all of f of x. So I'm going to put f of x in parentheses, 2x squared minus 3x. 3 times f of x, right? This whole expression is your function. Okay, then distribute through the parentheses, so you get 6x squared minus 6x. Oh, sorry, minus 9x. Careful there, multiplying all the way through. And that's it. Again, you can't do anything else with this. Can't simplify it. These are not like terms. You could factor a 3 out, but then you're right back to this. So that's it for these two. Okay, a couple more here. So the next one is saying, okay, we are plugging something into the function. We are plugging in a negative x. So again, it's going to be helpful if we think of this the way I had it before with the boxes. And when you think of boxes, you really want to think of, it's like they're parentheses. And this is saying negative x has to go in those two boxes. So we're going to have 2 times negative x squared minus 3 times negative x. The parentheses are representing the boxes. And now we simplify. We're squaring a negative x. So that square is going to wipe this negative out, but we do still have to square the x. So that's 2x squared. Then we have a negative times a negative on this one, so that gives us positive 3x. And that's it for that one. Can't combine like terms or anything. There are not like terms on that, so that's it. Okay, the next one, this negative I would say is inside the function. This negative is outside, meaning it's applying to the whole thing. We have to multiply the entire function by a negative. So I'll just write it out this way first. Negative f of x. So this gets distributed through the parentheses. You get negative 2x squared plus 3x. And that's it for that one. Okay, final one, or I guess second to final one. We're plugging in 3x into these boxes. So just like up here, but we're putting 3x inside of it. So this is 2 times the quantity 3x all squared minus 3 times 3x. Okay, we've got 3x in both of those boxes. So again, we need to apply order of operations here. We've got to be careful. This square needs to be applied to this entire expression, which means it's going to square the 3 and it's going to square the x. So we have 2 times 9x squared inside the parentheses there. And then we can multiply here, so you get minus 9x. And then to finish it, multiply the 2 by the 9. We get 18x squared minus 9x. And again, that's all we can do with that one, so we are finished there. All right, final one, and this will be probably the most important type of example. Most of the ones that we do when we get to the difference quotient will have at least a part that looks like this one. So again, it is helpful to go back to this little idea here. We are plugging x plus 3 into these two boxes. So the way that will look is 2 times quantity x plus 3 all squared minus 3 times x plus 3. Alright, and again, now we're just simplifying this. Now right here, this is where most of the mistakes are made. People think, oh, we'll just square the x and square the 3. But remember, x plus 3 squared really means x plus 3 times x plus 3, which means we have to use distributive property, or you can think of it as foiling here. So if we do that, we have x squared plus 3x plus 3x plus 9. And simplifying that, you get x squared plus 6x plus 9. If you remember the shortcuts for this is a perfect square trinomial. So the idea is you square the first, got that here. You multiply these two together, 3x, and double it. That's your middle term. And then you square the final term and put it here. So that's the way I will typically be doing this. I'm not going to write this out every time. We need to be comfortable just squaring these relatively quickly. All right, and then distribute the negative 3 and distribute the 2. And then this one, we do have some like terms that can be combined. We can combine the x terms to get plus 9x. And then looks like the constant terms just puts a plus 9 at the end of that. And that should be our final answer for that one. So the idea is we have evaluated this function at the expression x plus 3, and that gives us a new expression down here. All right, let's move on. Okay, so the next one says use a graphing calculator to evaluate these functions. So there are several ways we can do this on the calculator, but essentially all we're doing is we're taking this relatively messy decimal and just plugging it in. In other words, the first one is really going to be just 1.234 squared. I don't want to do that by hand, so I'm going to make the calculator do that. So give me a second, I'll pull the calculator up. Okay, so obviously one way we could type this in is just manually typing in the function as we had written before. And that works, but eventually we're going to get much more complicated functions. So a better way to do this would be to go to your y equals. If you have something in there, then you can clear it out. And then we can put in just the regular functions, so x squared. And let's hit on enter on that. That's not what I meant. Let's try that again. X squared. Hit enter. All right, so then quit out of here, second quit. And now what we can do is bring up the actual function itself and use regular function notation. So one way to do that, if you have the newer calculator, then you can use the shortcut alpha, and then I believe it's F4. So you get these little tabs here, and the this one here is the y variables. So you got all of your different functions that you can have stored in there. So we're going to just bring up y1, and we're going to use f of x notation. So we're going to do parenthesis and then 1.24, or sorry, 234. So this is plugging this into the squaring function. And you can see that is going to give us the same thing as what we had when we typed it manually. Same value. And for this, you're probably saying, well, that was a whole lot more work to do storing the function than to just typing it in. And you're right, but when we get more complicated functions, this is a much quicker way to do it. Now, another option, if you don't want to actually store it in there, then you can store just the value that you want to plug in. So the way we would do that is you start by typing the number 1, 2, 3, 1.234, and then we're going to store it as whatever letter you want. I'm going to use x. So now anytime you use the letter x, it's automatically going to plug in 1.234. So then we could just type out the expression using x instead, so x squared. Now the benefit of this is since we have multiple functions, we don't need to store any new functions, so I could just do the next one, 1 divided by x. And then the final one is square root of x. So this gives us all three of those decimal values on one screen there. Now, if you have an older calculator that does not have these shortcuts, the other way to get to the y vars is under the variable button here. If we press that, you can see right here y variables. So if I come over to that, they are functions, and then you see all of them here. So that would be another way to recall that function name. This again is still stored as that first one, so we're going to see it matches that value. If you wanted the other ones, then you'd either have to update this, or you could put them in the you could store them in the other spots here. Okay, so I'm not going to copy each of those over. You can rewind there and write them down if you want to. Okay, sometimes functions can be expressed in a way where the variables are on the same side, or where it's not solved where the y is not completely by itself. When it looks like this, where the y is not by itself, this is called implicit form. Many times, if it's in implicit form, you can then solve it for y and get the explicit form, which is generally more useful, but there are some times where this is preferred. So each of these functions are defined implicitly as functions of x, and then if you just simply do the algebra to solve them for y, it turns into these over here. There are some equations that cannot be explicitly solved for y, but we won't really deal with those until we get to calculus. Okay, so we're now at objective 3 here, finding the difference quotient of a function. So we did this last year, but like I said, the examples we're going to look at here are a little bit more complicated. So let me start by just going back through what is the point of the difference quotient. The point of the difference quotient is simply to find the slope of a secant line. So when you're doing this, you start off with some given function, y equals f of x. So that's this green curve that you see here. A secant line is simply any line that crosses the function in two different points. So we've got this red line is a secant line. It intersects the function here, and it intersects the function up here. And we want to find the slope of that line. Now, hopefully we all remember that slope is change in y over change in x. So we just need to find coordinates for these points and then plug them in. So we're going to start off with this first point, and we're going to denote the x coordinate just by x itself. The y coordinate, by definition, is f of x. Right? You plug the x into that function, and what do you get out? You get f of x. If we had called this point A, then this would be f of A. So whatever we call that x is what gets plugged into the function. Okay, now for this type of difference quotient, what we're going to do is we're going to say, suppose the other point, the second point, is h units away from this one. Right? It's either h units to the right or it's h units to the left. So to get that, that means this point would be x plus h if it was on the right, it'd be x minus h if it was on the left. Or you could just think of h being positive or negative, and that would take care of that. So the point is, though, the difference here, the distance here, is h units. So this x value is x plus h, the x value for this point, and that means the y value is f of x plus h. So these are the coordinates for this point, these are the coordinates for this point. If we have their coordinates, we can simply go back to the slope formula, do the difference in the y values divided by the difference in the x values. So if we take this to be y2 and this to be y1, then the numerator is just f of x plus h minus f of x, this minus this. The denominator would be this expression minus the x plus h minus x. You can see here that the parentheses are not needed on this, and then the x's just cancel, leaving us with this expression here. So the slope of a secant line for a given function is given by that expression, and that is also called the difference quotient. So those are the same concept. Difference quotient, slope of the secant, all the same thing. Okay, so I've just rewritten that up here, and so let's do that with, I believe there's 3 examples of this. All right, we're going to move this up a little bit here. So these do get a little messier. So we're going to start by just doing f of x plus h. All right, so that would be 2 times x plus h squared minus 3 times x plus h. This expression gets plugged into any place that you see x. Remember, the way that I think of the function is every x is an input box. And we're saying plug x plus h into the function, which means it goes in both spots. Common mistake is people just leave this as x in the second one, or they just put an extra plus h out at the end, and that's not what it's saying. It's saying take x plus h and plug it into anywhere you see the argument of the function. Okay, so now we need to simplify that. So again, remember here, you don't just get to square each one individually, you have to FOIL this. So let's, I'm going to do that without showing all the work there. We know that the middle term is going to be doubled, so it's 2xh in the middle plus h squared. All right, square the first, multiply the two together and double it. That's what I did here. Square the last. Okay, and then distribute the negative 3 through, so negative 3x minus 3h. And then distribute the 2, so 2x squared plus 4xh plus 2h squared minus 3x minus 3h. This entire thing is just this part of the difference quotient. So let's finish off the numerator. So the numerator is f of x plus h minus f of x, which is this expression. And then we're supposed to subtract f of x. Now this is another place where a lot of mistakes are made. We know there's going to be a subtraction here, but we have to subtract all of f of x, this entire expression. So the mistake is people just do this. They just write f of x, right? That's f of x. But you're not subtracting the whole thing. You're only subtracting the first part. So what we need is you have to have parentheses around that, right? This entire thing is f of x. So we're subtracting that entire expression. Okay, now obviously that distributes through to each of those terms, which I'm going to skip writing for right now, but if you look carefully at this, you'll notice that this term will cancel with this one. And then similarly, this is going to become plus 3x, so it's going to cancel with this one. You're always going to get a lot of cancellation when you get to this step. If you're doing it correctly, you should get some cancellation here, specifically when you're dealing with polynomials like this. Okay, so what we're left with then out of that is just 4xh plus 2h squared minus 3h, it looks like. Notice every term that's left has an h on it. For examples like this where you're dealing with polynomials, that's always going to happen. Every term at this stage is going to have an h. Okay, so now we're ready to write the full difference quotient. F of x plus h minus f of x, all divided by h. Well, we've already done the numerator. This represents the numerator. So 4xh plus 2h squared minus 3h, all divided by h. Okay, so now we just need to simplify. And you'll notice, like I said, all 3 terms in the top have an h, so we could factor that out. So that would be leaving just 4x plus 2h minus 3 all over h. Just pulled that out. This h then cancels with the one in the denominator. Right? Remember, to cancel things in the denominator, you really have to have it factored out. So that leaves us then with a final answer of 4x plus 2h minus 3. This expression is our difference quotient for this function. So in other words, what this represents is this is the slope of the secant line for any x value. You pick whatever x value you want, and then you pick how far over you want the second point to be. H represents the distance between the 2 points. So pick those two quantities, plug it in, and that gives you the slope of the secant. All right, let's try another one. Okay, so this one we can at least start it off a little bit quicker. So we're just going to go ahead and write the f of x plus h minus f of x. Actually, let's do the whole thing. Let's just go for all of it. Okay, so this one's much easier to plug in. When you see this function, this is the way I see it. 4 over an input box. We're plugging that into the input box. So this is 4 over x plus h. That's the first part. This is f of x plus h. Minus just the function itself. So 4 over x. And then the whole thing is over h. Okay, so you have lots of ways you could proceed with this. One way you could do this is you could multiply the numerator and the denominator by the least common denominator of these 3 terms. That is one thing that we did back in college algebra. You could also just perform the operation in the numerator, which is the path I think I'm going to do here. So I'm going to get a common denominator between those 2 terms, which is just the product of their 2 denominators. So, in other words, I want the denominator to be x times x plus h on both of those. Right, this is representing these first 2 fractions here. Go ahead and put the h down here. Now, in order for this denominator to be on this fraction, I'm missing the x, so the x would have to be in the top as well. Right, we really multiplied the top and the bottom by x. Right, we did x here and x here in order to make it look like this. Notice we're really just multiplying it by 1, so we haven't changed the value. Okay, then over here, you can see we're missing the x plus h, so that's what was multiplied on the top and the bottom. But remember that on the top here, this is going to have to distribute to both of those. So it's really 4x plus 4h. Okay, then we can go ahead and subtract. When you do the subtraction, again, be careful because this subtraction applies to both terms here. In other words, if I do this a little slower, this really says this. There's really parentheses around this so that that negative gets applied to all of it. All right, so it looks something like that. These 2 subtracted would look like this, and we still have that divided by h on the bottom. Okay. So let's go ahead and distribute the negative through to each of these terms. Notice those 2 are going to cancel. So what we end up with is negative 4h on the top over x times x plus h, all divided by h. Now I know you're thinking, ooh, we should distribute that. It's actually better to leave it the way that it is. Especially, this is a big thing that you do in calculus. You do lots of difference quotients, and when you do steps after that, and it's going to be much easier for you if you just leave things in factored form. So don't distribute. If it's factored, we like that. Okay, so what do we do here? This looks like a mess. So if another way to write this is it says this fraction divided by h. So let's write it that way. Using the old divide sign. This says the same as this. And we know that the definition of division is to multiply by a reciprocal. In other words, keep, change, flip. We're going to keep this the same. We're going to change that to multiplication, and we're going to multiply by a reciprocal. Division is multiplication of a reciprocal. In other words, and when we multiply fractions, we multiply them straight across. So numerators get multiplied and denominators get multiplied. So what ends up happening back here is this h really just ends up in the denominator. Right? We can see that right here. When we multiply across, the h is just going to end up in the denominator. So the more you do these, you don't have to show all of this. You should be able to just look at it and see, oh, that h is going to end up here because we're going to change this to multiply, and then it's going to be reciprocal. And then you can see those h's cancel. So you get negative 4 over x times x plus h. And that is your difference quotient for this. So it started off a little easier, cleaner at the beginning, but it did get kind of messy in here. Okay, one more of these. So we have the square root function. So again, we're going to go straight to the whole difference quotient. So first f of x plus h would just be square root of x plus h, and then minus f of x, which is just square root of x, and then that's over h. Okay, so this technically is the difference quotient, but they're going to want you to simplify this, and that's not really clear what we mean by simplify. Really what they mean is, in the previous two examples, you kept performing algebra until you were able to cancel that h that's in the denominator. We need the same thing to happen here. We need to be able to perform some algebra so that we can cancel this h. But it is not obvious what to do here. So this one has a trick. You want to remember for square roots, there's always a trick to this one, and it's the same one. And it goes back to something you did back in algebra, which we called the algebraic conjugate. So we saw if you took something like square root of 3 plus 5, and this is an irrational number. If you wanted to make it rational, then you could multiply by its algebraic conjugate, which is the same thing with the opposite sign. Whatever sign is here, you use the opposite sign here. When you multiply these, you would need to FOIL, so it would be square root of 3 times square root of 3, which is just 3. You would have square root of 3 times negative 5, which is minus 5 square root of 3. You would have 5 radical 3, positive 5 radical 3, and then the last one would be negative 25. Notice these two middle ones cancel. They always are going to wipe each other out because they're always going to be opposites, and then you can just subtract these two terms, which will give you negative, in this case, negative 22. Anytime you do this, you end up taking two irrational numbers and the product becomes rational. In other words, it gets nicer. It looks nicer. So we're going to apply that same strategy here. It's not really clear why we want to do this. I'm just telling you it is going to work. It's going to make it nice. It's going to rationalize this numerator. So the conjugate here, the algebraic conjugate, would be x plus h plus square root of x. Now, we can't just multiply by this because that would actually change the value of the expression. So we're going to have to do the same thing to the bottom so that what we're really multiplying by is 1. Right? This expression really represents 1. So when we multiply it by this, it does not change the value. Okay, so then we're multiplying fractions, so we multiply the numerators together. And notice that these are binomials here, so we're going to have to FOIL just like we did here. But the same thing is going to happen. These two middle terms, when you multiply this by this and this one by this one, those are exact opposites, and they're just going to wipe each other out. So the only thing you really have to multiply is the first two terms and the last two terms. When you multiply the first two terms together, the square roots will wipe each other out. Square root of x plus h times square root of x plus h, that is just x plus h. Right? Anytime you multiply two square roots with the same radicand, you just get the radicand. So that's the property we're using there. Okay, then you need to multiply the last two terms. And again, same thing's going to happen. Square root of x times square root of x, that's just x, but we do have a negative here and a positive here, so it's minus x at the end. All right, and then the final one, we multiply the denominators, and you're going to be tempted to distribute it to both, but again, don't distribute. Leave it on the outside. Leave all this big nasty stuff on the inside. Okay, so it's just h times all of that. Now go back to the numerator and you'll notice this x and this x cancel, so it just leaves an h in the top. So we get this expression. And now we can see those h's will cancel. But that doesn't mean the top is 0, right? Your h over h is really 1. So there is a 1 that's left in the top. And then you still have these square roots in the denominator. I copied that wrong too. These should be pluses. Right, I just copied it over here. All right, so we should end up with that expression there. So that is your difference quotient for the square root of x. It requires this conjugate trick. Now, my guess is if I lost you anywhere, it's with this part here. So what I would like you to do, if you got lost with that, come back here and actually do FOIL, write it out carefully, and simplify it, and you will see that it comes out to this. Okay, so moving on to the fourth objective, we're looking for the domain of functions defined by equations, and here's the general process. So the domain, remember, is the set of all inputs. So we're going to start off, when you look at a function, you're going to start off and assume that the domain is just everything, meaning all real numbers. The domain is all real numbers. Then we're going to figure out maybe there's something that needs to be thrown out. So to find the things that have to be thrown out, the first thing you look at is, are there any denominators that have variables in them? If there are variables in any denominators, you need to exclude any number that makes the denominator 0. You can't have division by 0, so that's the first place we look for things that need to be excluded from the domain. Then the next thing we look for are radicals, specifically roots, even roots. So square roots, fourth roots, sixth roots, eighth root, anything that's an even root. We can't take even roots of negative numbers. That would give us imaginary numbers. And for this class, at least for now, we're not dealing with any complex or imaginary numbers. We need everything to be real. So if you end up taking a square root or a fourth root of a negative, that whatever value of x made that radicand negative needs to be thrown out. And then the final one is dealing with logs. If you have any logarithms in your function, we can't take logs of 0 and we can't take log of negatives, meaning that the argument of the log, if anything that makes the argument of the log non-positive, has to be thrown out. So I call these things bad behavior. So the bad behaviors that we can't have is division by 0, even roots of negative numbers, and logs of non-positive. Any x value that would make any of these things happen has to be thrown out of the domain. All right, so let's do some examples. Okay, so first one, this is a polynomial function. So let's go through. We start off with the assumption, okay, we're going to let all real numbers be the domain and see if anything bad can happen. First one, are there any denominators? No, there's no denominators here, so we don't have to worry about that. Next, are there any roots, any radicals for this? There's no radicals, so don't have to worry about that. And then third, are there any logs? No logs in this function either. So it doesn't have anything that could cause bad behavior, which means its domain is all real numbers, which you could write as an interval, negative infinity to positive infinity. You could do the double struct R for all real numbers, or you could write out all reals. I believe MathXL is typically going to want that notation though. So you are probably all screaming as soon as you saw this, because we know this polynomial function, and one nice thing about polynomials, all polynomials, their domains are always all real numbers. Okay, next one. This is a rational function, polynomial divided by polynomial. So immediately we do have a denominator, and that denominator could cause a problem. We can't have the denominator being 0. So let's figure out when it is 0. Anything that satisfies this equation has to be thrown out of the domain. So if we look at this, we notice, ooh, this is a difference of squares. This is really x squared minus 2 squared, which hopefully we remember that has a special factoring property. This is x minus 2 times x plus 2. So then using zero product property, we see the two solutions are 2 and negative 2. These cause bad behavior. When you plug those into the original, you get division by 0, so they must be excluded from the domain. Okay, so the domain, we can write this in several ways. We can do this with set builder notation, set of all x such that x is not equal to 2 and x is not equal to negative 2. Or we can do intervals. So the intervals would be, if you think of a number line, we got negative 2, we got 2 here, and those have to be excluded. So we start from the left and go to the right. So we're going to start at negative infinity, We can go all the way up to -2, but we cannot include it, so we use a parenthesis. Union, the middle interval, -2 to 2. Union, 2 to infinity. Either notation is acceptable. I prefer this, but I do believe MathXL is going to do mostly this, at least at the beginning. Okay, we don't have to worry about the other two cases. There's no logs and there's no even roots on this one. Okay, next one. So we can see square root right away. So the radicand, which is just what's inside, this expression can't be negative. It can be 0, but it can't be negative. So what we need is we need 4 minus 3t to be greater than or equal to 0. The radicand has to be greater than or equal to 0. Common mistake people make with this is they leave the square root in there, and it's not a big deal on this one, but that's really, you're looking at it the wrong way. We don't care necessarily if the square root is negative. We need the radicand, just what's inside it, to be positive. We don't care if the square root itself is positive. Okay, so if we solve this, add this over, 4 is greater than or equal to 3t, and then divide the 3 over, so 4/3 is greater than or equal to t. This is our domain, really. I'm going to flip it around, just flip the inequality around. Make sure you preserve the order that it's actually stating. T is smaller than or equal to 4/3, which this says the same thing. And we can just turn this right into set builder notation. Set of all t such that t is less than or equal to 4/3. That's your domain. Or we could make this into interval notation. So if you've got 4/3 here, we want values that are less than or equal to it. So we want this side of that number line. So we're going to have the domain being -infinity up to 4/3, but the 4/3 is included, so we use a square bracket there. Okay, final one of these. This has got two places where bad behavior can happen. We could have division by 0, which is not good, or we could have a root of a negative. So we have to do two separate things. So obviously we set this equal to 0, set the denominator equal to 0, you get x equal 5. This has to be thrown out of the domain, right? So maybe it's better for you if you actually write it like that so you don't forget x can't be 5. The other thing that we need is we need the radicand to be greater than or equal to 0, just like this one. So you take what is under the radical sign, greater than or equal to 0, and solve that. So we've got 3x greater than or equal to -12, divide by the 3. X has to be greater than or equal to -4. So if we think of this as a number line, we got -4 here, we've got 5 here. So it's saying it can be 4, but or anything greater than 4, except it can't be 5. 5 has to get thrown out. So graphed as a number line, it would look like this. This is our domain. So you could do it with set builder notation. It's the set of all x such that x is different from 5 and x is greater than or equal to -4. Or we could do intervals like we did over here. So it would be a bracket there. -4 is included. And then up to 5. 5 is not included. Union that with 5 to infinity. Remember, we never put brackets on infinity. So this is indicating, since both of these are parentheses here, that's giving us the whole here at 5. 5 is excluded from that domain. Okay, so this example says express the area of a circle as a function of its radius and then find the domain. Now, as soon as you see this as a function of its radius, that means that radius is input and this must be output. Another way to write this then is if area is the output and radius is the input, it's A of r. Area is the output of the function, radius is the input. Well, we know the formula that goes with this. Area is, hopefully we know this, pi r squared. This expression, if you plug in the radius, it will spit out the area. So that's our function, the area as a function of its radius. So then it says find the domain. Now, if we just think of this as an algebraic expression, the domain would be all real numbers. Because it's polynomial, there's nothing bad that can ever happen. However, this function has an application. It has a meaning. So we need to think about, well, what kind of different radii can we have? Does it make sense to have negative radius? No, it doesn't. Does it make sense to have a zero radius? Well, I would argue that we could, but according to our book, they don't want you using zero radius here. So the domain that they're looking for is non-negative numbers, meaning 0 to infinity, but 0 is not included. That would be your domain. So we got our function and we got our domain. Okay, last objective is to form the sum, difference, product, and quotient of two functions. So I've got them defined here. These are what we call point-wise operations on functions. If you want to take f and add g, the definition of that is to just plug x into f, plug x into g, and add the two functions together. So as an example, just to make sure we're clear on this, let's say f of x equals 2x plus 1, and g of x is equal to 3x. If I wanted to do f plus g of 5, the definition is f of 5 plus g of 5. So you would plug 5 into the first one, which we can see is 11, plug 5 into the second one, which you can see is 15, and then you'd add those two together. Point-wise addition. So this would be 26. Same thing with subtraction, same thing with multiplication, and same thing with division. The thing we have to be careful with division is to make sure that you need to throw out anything that makes the denominator equal to 0. Okay, so we're supposed to apply these operations to get a new function, and then also find the domain in each case. Okay, so according to this, it is just f of x plus g of x, which is equal to 1 over x plus 2 plus x over x minus 1. Now, technically, we've answered the problem. It said find the function, we found it. But if this were a homework problem on Math Excel, my guess is they're not going to give you credit for this, even though we have technically done the work. What they really probably mean is find the function and simplify. So they want us to simplify this expression. So to do that, we need to actually add these two rational expressions together, and we'll need a common denominator, which again is just going to be the product of the two denominators. So x plus 2 times x minus 1 is going to be the denominator on each of them. So the first one, it's missing the x minus 1, so that needs to be in the top. It'd be 1, really it's technically 1 times x minus 1, so that these cancel and it would take you back to that. And then this one is missing the x plus 2. Right, the x plus 2's cancel, which takes you back to that. Okay, so now the numerators match, or sorry, the denominators match, so we can go ahead and add the numerators. So we would have x minus 1, this 1's not doing anything, so I just dropped the parentheses and the 1, and then in the second one I'll go ahead and distribute as well, so it's really x squared plus 2x, and then again, don't multiply out the denominator. It's factored already, leave it in factored form. Be careful with that, it looks like a plus, that's supposed to be a minus. Okay, and then we can combine like terms in the numerator. So we end up with x squared plus, looks like 3x minus 1, and leave the denominator as it is. Alright, so that's our function that you get from adding them together, but it did also say identify the domain. Now, one of the main reasons I tell you not to multiply out the denominator here is it's already telling you what the domain is. This is a rational function. The only bad thing that can ever happen is division by 0, and what numbers would give us division by 0? Well, for this first factor, negative 2, and for the second one, it would be positive 1. So we need to throw those numbers out. It's the set of all x such that x is not equal to -2 and x is not equal to +1. Those numbers give you division by 0, so they have to be thrown out. We could also see those numbers back here. Even without doing all of this, we could see it here. So really what this is, it's just the domain of f intersected with the domain of g. Okay, if we do the next one, it's going to be the exact same procedure. And you're going to get a common denominator in the exact same way. So I'm actually going to kind of skip some steps here. So all of this is going to be exactly the same, except this will become a minus sign over here. So we can actually go straight to what the subtraction would look like. It would be x minus 1 minus x squared minus 2x. Notice this subtraction is because I would have to distribute it to each term here. Right? We're subtracting that entire expression, which is an x squared, and we're subtracting a 2x. And then the denominator is going to be exactly the same. Okay, so if I went too fast there, just come back and actually carefully do the same steps, but with the minus sign, and you will see you get back to this same thing. And then if we clean up that numerator, that's negative x squared minus x minus 1 over x plus 2 times x minus 1. All right, so then domain, well, it's going to be the exact same thing as over here because the denominator still has the same factors in it. So it's the exact same set. It's a set of all x such that x is not equal to -2 and x is not equal to 1. All right, so that handles addition and subtraction. Let's look at multiplication and division. So it turns out multiplication is going to be easier. Really, both of them are easier. So this definition of this is f of x times g of x, pointwise multiplication. So it is 1 over x plus 2 times x over x minus 1. When we multiply rational expressions, we just multiply numerators and multiply denominators. You don't need anything common, you just multiply across. So the numerator is x, denominator is x plus 2 times x minus 1. And don't FOIL that. There's a chance that MathXL might force you to FOIL that, but I would never do that. It's better to leave this factored as it is. And again, the reason being, it immediately tells us the domain. Just like the previous one, x can't be -2 and x can't be +1. So set of all x such that x is not equal to -2 and x is not equal to 1. Alright, so that takes care of multiplication. Let's look at division. So this one, it's not bad, but we do need to be careful here. So this says f of x over g of x. Now, you could write this write it out as a complex fraction here. So this is really what it says, f divided by g. But we know that division means multiply by a reciprocal. Right? This could be written as 1 over x plus 2 multiplied, let's go carefully here, divided by. That's really what this is, this divided by this. But we know that when we divide, it's the same as multiplying by a reciprocal. So again, that's keep, change, flip. If we're taking this and dividing by this, keep the first the same, change this to multiply, flip the second term there. And now we're doing the same steps that we did over here. Multiply the tops, so the top would be x minus 1. Denominator would be x times x plus 2. Alright, so that gives us that. Alright, now, when you look at this, you're thinking, okay, the domain is just we're gonna throw out 0 from this, and we're gonna throw out -2 from this, and that's it. But we gotta be more careful. With division, you gotta be more careful. we got to come back and let's look at the original expression, right? This original thing here is, what are the numbers you can't plug into this? Well, you can't plug in -2 because right here you'd have division by 0. But down here you can't plug in 1. Right? 1 was excluded from the domain of g. There's no way to evaluate g of 1. But you can't see that here. It looks like you can. Because of this simplifying, that got hidden. You can't see that part anymore. So you need to go back to the step before you did any simplifying at all and ask yourself, what is the domain of that expression? Now you can also see where the 0 is showing up, because if you plugged 0 into this expression, that would make the entire denominator of this big fraction equal to 0. So that's why we have to throw out 0, but you can also see it easily from this term. Okay, so domain is, make sure we get them all. We can't have 0, set of all x such that x cannot be 0. X can't be -2. But then we can't forget this guy, the one that made g of x 0. Anything that would make, or g of x undefined, which is x equal to 1. Right, that made this undefined, so you can't plug that in. So that has to be thrown out as well. 0, -2, and 1. If we were going to write this as an interval, think of it as a number line. We've got -1, 0, and, oh, sorry, I got those backwards. It was -2 and a +1. Okay, so we're going to write it as an interval. It's just those three numbers thrown out. So you've got 4 intervals here. -infinity to -2, union -2 to 0, union 0 to 1, and then union 1 to infinity. So those would be the 2 different ways that you could express that domain. Alright, so that handles the different operations. I guess I should circle that. That was our simplified function. And I think that concludes this set of notes. So if you have any issues with the homework, make sure you are sending me your questions, and good luck.